Hi there, John Beverly here, instructor for logic, symbolic logic that is, and we are today covering in a little detail this language that we've been playing with called L3, which is our quantifier logic, the quantifiers being universal and existential additions with predicates with arities in our language. So what do we have in more detail with respect to syntax? We have everything in L1, everything in L2, plus we get universal quantifier, we get existential quantifier, we get some variables, so forth, and so on. This allows us to essentially count things in our language. As long as we, and of course we construct formulae with that in mind. Now, as with every logical theory, we'll have the syntax, which is what I just described for L3. We'll also have the semantics, and then we'll have a proof theory associated with it. Now, we've been for several days, several sessions, as a matter of fact, discussing the semantics. This is to say, what are the meanings of the symbols here? How do they work together? And how can we construct, in our case, interpretations that tell us when certain expressions that are built up out of these symbols are true and when they're not? And so then interpretations are the way we've been doing this. Interpretations that consist of content of the following sort. We identify a domain, we identify extensions of our predicates, so things like, e.g. P one place means is a parrot. We also give extension or identify what it means to be an extension of constants like lowercase a. We'll say that's something like Alex. Perhaps Alex is a parrot. If we wanted to write that in our language, we'd say something like that. Alex is a parrot. And if we wanted to say something is a parrot, we'd say something like something is a parrot, or everything is a parrot, and so forth and so on. Essentially showing you what it means, again, to construct more complicated expressions out of simpler ones on the one hand, but also to say when these expressions are true and when they're false, namely under the scope of some interpretation where we've assigned these constants and these predicates values. So we've spent, again, a lot of time doing this interpretation stuff, drawing pictures, do like little smiley faces like this. I said if I had like a little image of this sword with an interpretation that said, Alex was a parrot, Bob was a bear. This might be how we characterize this in our diagram. Of course, if I wanted to say this parrot is taller than that bear, I might draw a little line there. We've got two place relationships, and this could say Alex is taller than Bob here. Again, straightforward. Spent a bit of time on that, but now, I'll just put interpretations here. Now we're going to be discussing the proof theory. So this system, L3, as with L2 and L1, they are all sound and complete. That is to say, if you can prove something in the language, then it's true in an interpretation, and if you have something, an interpretation that's true, you can prove it. And what am I talking about when I'm talking about proving? I'm talking about preserving truth from the premises to the conclusions of arguments. So logic is fundamentally concerned with argumentation. How do you move from a set of premises to a conclusion? Absolutely be sure that moving from the one to the other preserves some value. A value we often like to preserve is truth. So if I have a sentence like, all men are mortal, all mortals die, then we want to be able to say, as a matter of logic, that all men die, and so forth, and so on. As far as I understand, this is true. As a matter of fact, if the premises are true, the conclusion is true, And that's what we're trying to characterize here when we're talking about validity. If the premises are true, then the conclusion is true. And validity is this formal feature of arguments that we want to be able to characterize in L1, L2, and L3, and that's because it gives us the meat, as it were, to be able to say things such as, if we can prove it, then it's true, and if it's true, then we can prove it. And what that back and forth is if we can prove it, then it'll be valid. If it's valid, then it's preserving truth from the premises to the conclusions, and we can show that. And if it can preserve, if there are arguments that can preserve or do preserve truth from premises to conclusions, those are the sorts of things we can prove. That's what it means to be sound and complete in our language. So, again, we've been playing around with interpretations. Now it's time to play around with the proof theory. So I discussed a little bit, I kind of gave you a little teaser of this, whet your appetite as it were, but much like with all of the other connectives in our language like conjunction, disjunction, material conditional, negation, at least in its double negation forms, all of these have intro and outro mechanism. So you have an introduction rule for conjunctions. Anytime you have something of this form and something of this form on a line, you can infer, and then on the third line, as a matter of logic, this. So if phi is true on one line, if psi is true on another, then you can infer phi and psi. That's how you can introduce conjunction logically. And if this is true and this is true, then this has to be true. Validity. We also have outro rules, so you can eliminate this if you have phi and psi. Excuse me. And psi, then you can infer as a matter of logic phi. Or you can infer as a matter of logic psi. Same idea. If the premise is true, then the conclusion is as well. We have intro rules, outro rules for disjunction. We have intro rules, outro rules for negation, although it works a little different. If you have not phi, then you can infer phi. Similarly, if you have phi, then you can infer not phi, because if first is true, the first premise is true, the conclusion has to be true in either case. Now, the only one that has a slightly different rule is going to be material conditional, of course. We have modus ponens. If phi, then psi, and phi, then you can get psi. And this is a way of breaking or eliminating the material conditional there. As discussed, we couldn't actually come up with a simple rule to introduce a material conditional in our language. And why is that? Well, think about what's going on. Say I want to show or prove something of this form, P, then if Q, then I'm sorry, I should have written Q there, then P. Now, if you recall, I'm trying to prove this from no premises, so this is a tautology. It is always true. If it's always true, I should be able to prove it from no premises. As a matter of fact, I can. But what I have to do in doing in such a proof is somehow introduce a conditional. Now, how do I do that? Well, the way we've described in class is that we make an assumption. So you assume something. For the sake of argument, you introduce a new show line. And whatever the new show line is whatever is following that thing you assumed in the conditional. So you assume the first part, the thing the arrow is pointing from, and then you try to show, using other rules that you have, that the second part follows. Now in this case, it's a good example, highlighting kind of repetitively what we have to do, because the methods we have to use to introduce conditionals, because we have to do this again. We have to once again assume Q, because it's the first part, because we want to prove this conditional, and then we right below indicate that we want to show P, right? And so now, of course, it's a little easy to see how the proof goes. We want to show P. Well, it's easy to do. We already did. So since we showed P, we can just repeat that down there. Boom, we're done. We box that up. Now we were trying to show if we assume Q, we could get P. We did that. So boom, we box that up. And now we were trying to see if we assumed P, then we could get if Q then P. So we can box that up and drop that show line, and now what we have is a bunch of embedded proofs with assumptions in them, showing how we can, with a little bit of calculation, show if P, then if Q, then P. Now, again, I said we don't have a simple rule for introducing conditionals. It's because we have to assume something first. And in this case, I assumed the first part. I assumed P, and then I tried to show the rest. But technically, you can assume whatever you want. Like, there's no restriction here on what you can assume. Assuming can make, something out of you and me, as they say. We try to restrict our assumptions to the first part of the thing that the arrow is pointing from the main connective, as a way to kind of focus in on that broad power we have to just assume anything. You literally can assume anything, any formula, anything. It might not get you where you need to go. It's helpful if we just kind of target something that we're trying to assume and then show what follows in the back end. But because of that kind of power built into the method, we don't have a simple rule. We can't just say, look, there's a pattern. Always follow that pattern, and that's how you introduce a conditional. We have to create another method of proof, namely, we get to choose to assume something. What do we assume? This right here. So, and the method itself is like built into it is focus on the thing the arrow is pointing from in your assumption. That's the rule. But it's not the same kind of rule of the form that we had in the previous connectives, where it's just like anytime you see this, write down that, because of that assumption. Now I know this is old hat, and I've told you this before, but it's going to be important because we're going to have to introduce a new method of proving when we're introducing universals in our language. So we have intro and outro rules, or intro and outro strategies for universal and existential expressions. And so we have, say, universal elimination, universal introduction, existential elimination, as well as existential introduction. So intro, outro. If we get somewhere, we want to be able to get out of it. So two of these are easy, two of them are less. Universal elimination, pretty easy. Here, let me give you a simple example. So I have as an assumption, everything is a parrot in my domain, and I want to show that Alex is a parrot. Well, how do I do that? What follows? What do I do next? Well, I'll tell you what I do. I just write down on line 3 that Alex is a parrot, and I cite line 1, universal elimination. Why? Because line 1 says everything in my domain's a parrot. That means Alex is a parrot. So it's pretty easy for me to show Alex is a parrot because everything's a parrot. That means everything. Quantifier's open. No restriction on that universal. It means everything in the domain. Now, well, the way we talk about this, and you'll hear me slip into it, is that I'm kind of instantiating the universal variable to a constant. So in this case, I have instantiated to Alex, right? So I've gotten rid of the variable, gotten rid of the x, gotten rid of the quantifier, instantiated to a specific constant, a specific name, Alex. Now, we just have a rule for this. You just drop off a universal anytime you want because it covers the whole domain. So check there, easy peasy. What about easy one here, existential introduction? If I have on a line that Alex is a parrot, and what do I do if I want to show that something is a parrot? I know, drum roll, please, I'm sure you're thinking very carefully, what am I possibly doing? Don't think too hard, because all you have to do is infer from one existential introduction, Alex is a parrot. Or from Alex is a parrot that something is a parrot, because it absolutely follows that if Alex is, something is. Remember that existential just means anything. Anything would satisfy. And Alex is a witness for it. Anything else could be as well. We've got Alex, we can cite him. We didn't need to do any instantiation. What did I do? I wrote an A there. You guys got to watch me on this. You just instantiate. You don't need to instantiate, that is. You can generalize, as they say, over the existential variable in the domain. So if he's the witness, surely something is a parrot, and that's an easy rule to introduce. So again, two easy cases, two less easy cases. So before I get into the less easy cases, though, I want to go through some examples, perhaps stumble upon the harder cases as we go, but just in the interest of giving you something to play with, or giving you, I guess, examples that you can learn from, and then watch me draw over here, because I know that's really what you came for, just to watch me doodle. Let me look at some examples here. Fx and then Gx. What I'm going to do is I'm going to show you how our rules combine with some of the more familiar methods and strategies that we've been playing with in L1 in particular. So if I have, say, for everything in the domain, if it's F, then it's G, as one premise, and then line 2 I have Bob is not G. I want to show that Bob is not F. Let's think about this for a second. Doesn't it make sense? Everything, for everything, if it's F, then it's G. And so Bob is not G. Shouldn't it be the case that Bob is not F? If it were F, it'd be G. If it's not G, it better not be F. Now, how do we prove this is the thing? So I'll tell you what. Universal instantiation. Just drop that thing off. You can instantiate directly to B. And we just cite one universal elimination. Now, what do we have here? Well, we've come up with a rule. We've identified a rule before in our language, at least in L1. We can apply it here too. I'll just write it up. It says something like a parallel a bit of modus ponens. We call it, because we love Latin and hate common sense, modus tollens, or MT for short. The textbook calls it something like material out, something of that sort. We'll stick with modus tollens because I'm pretentious. Anyway, but remember, these psi's, they are meta variables that can be anything, including expressions of this sort. So what I have here is I have if FB, then GB. I have not GB. That allows me to infer not FB, and I can just cite 2 for modus tollens. Dunzo. Box it up. I've proven this. So you see our rules that we've already familiarized ourselves with interplay, just as you would expect, with the universal rules that we're introducing. So this intro, outro, as we will see. And we look at another example, something that might be a little meatier. Let's see. Let's play with this bad boy. I'll start it at the top. I want to say everything. I'm going to use a relation here. And here we'll say for any x, any y, rxy, then rxx. Ooh, I wonder what we can infer from this. And then we'll also assert not fa. and then we'll show. What do you think we can show? Not A, B. What an interesting development. You see, I've got A on line 3 in the premise. I have no B in the premises, but I do have a B in the show line, so I have to show something. I have to show something about a constant in the domain, something in the domain that I'm not talking about at all in the premises. Now, how can I do that? Dun, dun, dun. I'm sure you're ahead of me here. Again, I can instantiate the universal to anything in the domain. As a matter of fact, everything in the domain, and that's exactly what I'm going to end up doing here. So I'm first going to go to RAA. I'm just going to drop that. I'm going to put FA here, and that's line 1, universal elimination. Why did I do that? Well, because I can use not FA on line 3 to infer not RAA here, and that is line 1 and 3, and that's from Modus Tollens, our friend we just encountered. Now, I still haven't gotten exactly where I need to go. I'm trying to get not RAB, not RAA. So what's up? Well, I'm going to drop off this. I'm going to do some like careful instantiation here. I'm going to drop off the x's first. Instantiate here to on line 7 to for all y get r a y, if that, then r a a, and that'll just be from line 2 universal elimination. Note what I did, I just dropped off the x, and you'll note x y x x, so this x is binding that x and those two x's. This y is untouched. I just dropped off one of the quantifiers here. So now on line 8, what I'm going to do is I'm going to drop off that quantifier, universal, and I'm going to instantiate it to B. And now I've got if RAB, then RAA, and that comes from 7, universal elimination. Why did I do that? Well, check this out. On line 9, if I connect that not RAA with line 8, then I can infer not RAB. Using what? Our old friend again, is at 6 and 8, Modus Tollens. Now, there's our nice little proof. I'm going to box this carefully. Boom, show line. What we know, we've proven from these premises, we can infer not RAB, and we've done it by dropping off and instantiating a little carefully our universal quantifier into a couple of different places. So, now, I do want to highlight next, let's see, maybe another example here, one that connects up these two easy cases of quantifiers, so that you can see how that introduction of existentials also works. I'll pick this example. We'll say on line 1, universal x, rxa, if that, then not rxb. That's our first premise. On 2, we'll say raa. And what we'll do is we'll say, I want to show there is something such that it's not RXB. All right, now how are we going to get this? So, you see I have an existential I'm going to have to introduce here. I can be able to just pull it out of the premises directly, but what I can do is I can instantiate that x to A, and then what I'm going to get is not, if RAA, then not RAB, and that's line 1, universal elimination. Now, why did I do that? Well, look, I already have RAA there. This is our friend Modus Ponens that we can use here. It lets us infer not RAB, so that's 2 for Modus Ponens. Modus Ponens, of course, is this bad boy. infer that validly, that rule. You see that on display here. And so from here, what we can do is just introduce our existential quantifier over the A place, so that we have Rxb, which is what, oh, I'm sorry, I forgot the negation, not Rxb, which is what we were trying to show, and that is from 5, Existential Introduction, boom, did it, proved. All right, how you feeling about that? You want something harder? I get it. Now let's see how these rules play with another method that we've seen before. The biggest method, the granddaddy of them all, indirect derivation, where we assume something is true, try to find a contradiction, and when we do, take back one of our assumptions, whatever that was. Because remember, everything in our language is true or false. Nothing in our language is both. So if we ever get something that is both, we've gone wrong. We've got to take it back, and because everything is true or false, we just take the opposite of it. So what I've got here, two premises. If something, or if A is related to something, then everything is related to A. I've got not B being related to A, and what I want to do is show that it's not the case that A is related to A. Okay, so how do I do this? Well, first, because it's not clear how, I'm just going to like fiddle around with the premises. I'm going to have to do something a little clever. So I can't like get rid of the existential. Like, I don't know what to do. I don't have a rule that tells me how to get rid of that existential. I can't do anything with RBA. Most I could do here is introduce, something that looks like this. Our existential x not, say, bx. That doesn't look, ax. That doesn't look like it needs to. It's got a negation in there. I don't even get the existential instantiation correctly. So I don't know what I'm supposed to do here. All I know is that when I get stuck, typically, I assume the opposite of whatever I'm trying to prove, and I see what happens. And so here, what that looks like is I'm going to assume RAA, and I'm going to see if I can get some kind of contradiction. And this is an assumption that I'm making for indirect derivation. So I'm going to try now, just to make this super explicit, I'm going to try to show a contradiction. And we typically will highlight contradictions by using this exclamation point, because as I've noted before, I have a flair for the dramatic. Now, what are we doing next? So like on 6, what I'm going to try to do in deriving or constructing this derivation is I'm going to infer from here, there is something such that RAX, and what am I doing? I am taking line 4, and I'm doing an existential introduction just into one of those A places. I don't have to do all of the constants at once when I'm instantiating. It is totally up to me. If I have something of the form RAA, that I can just infer RXA, and then do something like I'm free to do that. It should make sense, because if I had something of the form RAB, I'm not immediately bound to say something like that, right? Of course I'm not. I could do that, right? Of course. Same deal here. The A, they're in different places. You can instantiate them separately, and that's what I'm going to do here. Now, on line 7, I'm going to now use one here in combination with that, and I'm going to infer RXA, and this is just our good old friend 1,6 Modus Ponens. Now it should be pretty clear where I'm going. Now I can drop off the x, instantiate that to b, right? Because I can do that. That's from line 7, universal elimination. Why would I do such a crazy thing? Well, easy to see if I drop line 9 down and show that I've got a straight up contradiction, line 2 and line 8. Bang. Bum, bum, bum. Now, that means because I got a contradiction, I got to take something back. I proved the thing. I proved something inconsistent. It can't be both true and false. It's got to be one or the other. On that, it was on this assumption, so I assumed RAA got a contradiction. I went wrong somewhere then because there are no true contradictions in our language. That means I take back what I was trying to show. Incidentally, I did this bang demonstration using just direct proof methods, just moving symbols around. But here I used an indirect derivation method. I assumed something for the sake of contradiction and then proved a contradiction. And now I had to take it back, basically. All right, so let's see, what else can I demonstrate for you poor unfortunate souls? Let's see, something juicy. While I'm doing this, just stare at the proof, make sure that you've got a handle on it, and I'll try to find you a slightly more challenging example to illustrate some of the problems or the issues you might encounter as you're proving things. So, is there anything really that challenging, or is it just really easy and straightforward when we're dealing with these intro-out rules that are, or intro/outro rules? It's kind of that. And they're not too complicated. When it gets complicated, we'll see as we enter into the other two rules we have, where we're eliminating existentials and trying to show universal statements. So, as I said, easy versions, not so easy versions of these rules. The not so easy versions of these rules, one of them is the existential elimination. So mark here, and what this looks like can be demonstrated in something like this. Suppose I have an argument of this form. I want to show that from something is a parrot and something is a bear, that it follows that something is a parrot. So, from the premise, something is a parrot and something is a bear, I want to show that something is a parrot. Now, it seems like it's exactly the sort of thing I should be able to show. Now, note though, I don't have any rules that will let me just break off or get rid of that existential. I'm going to have to do something like instantiate it, much like I was doing with the universal quantifier. I can't instantiate the existential to just anything. I just can't. Universal means literally, if I say everything's a parrot, anything's a parrot. Anything in the domain's a parrot. I can't do that here. I'm saying with the existential, something's a parrot. I don't know what it is. I don't know if it's Alex or Bob. So I can't just willy-nilly instantiate to my heart's content. What I can do is I can essentially just kind of like pick an arbitrary constant and drop off the existential for that. I can pick A, for example. Now, why can I do that? Why can I instantiate using existential elimination on line 1? Why can I instantiate to A? Well, check it. A has not appeared in a previous line of the proof. At no point do you see A up here. It ain't happening. I don't know anything about A as far as this proof is concerned. I could pick B. I could pick C. I could pick a rose or a star. I don't know. I don't care. It doesn't matter. I know nothing about it. I could replace, in any of these cases, A with B, A with C, whatever, And that's because I don't know anything about it. And the way I would know something about it is if I had it in my premises or I'd proven something about it, and I just haven't. So I can pick this arbitrary constant. It could have been any other, and then I can use my normal proof rules from here on 3. That's conjunction elimination, and I can introduce an existential just from the easy case, right, for existential introduction here. Boom, boom, boom. And I did that by direct derivation. Now, see, I got rid of it, I proved something. Could have been about Alex, could have been about Bob, but basically the idea is like structurally I instantiated the existential to some individual. I proved something, I moved some symbols around, and I was being able to infer something else based on that symbol manipulation. In this case, I boxed up this proof, and you know what that means. That means it's gone, right? Like I've done it, it's out. On this, it's like I've assumed, created a little space of a proof and then put it aside. That's why I box it up and mark it off. Because really I've just shown I could have done this with anything, B, C, D, whatever. And this is the heart of existential elimination, right? I can do that. I can drop off these existentials just like that. Now, the other, that's one side, right? We have also a need to introduce universal expressions. We need to be able to prove those things. That is the other side, the other difficult way or problem that we have, or difficult rule that we have. And in fact, it's not even a rule. It is much like with indirect methods, much like with direct methods, much like with conditional proofs. It is a different method. So we have a universal derivation method, and that is how we prove universal expressions. Let me show you. If I have something of this form, if px, or for anything that's px then gx, anything that's gx then fx, it should follow from that. Make that a little cleaner. Should follow from that. Oh, I just missed all the. Try that again. It should follow from that, and we'll demonstrate that it does. That for all x, if px, then fx. This is just transitivity. So for everything, if it's px, then it's gx. If it's gx, then it's fx. It better be the case that if it's px, then it's fx. So how do I pull this bad boy off? Again, we'll have to introduce a new method for proof. So we call it universal derivation. What do? You just pick an instantiation. In this case, I'll just pick A of FA. Now, what am I doing here? I need not just to put PA and FA. As a matter of fact, I need to show that if PA, then FA. Now, a couple of things going on here. I did this by picking a constant, A, to instantiate to that has not appeared in a previous line. It's the same setup. I don't know anything about A here. It's not appeared previously, and it's important because if I knew something about it, I would be kind of importing too much information into a proof about everything in the domain. So it really should be arbitrary because I'm trying to show something about everything in the domain. I'm trying to infer this. So that better be arbitrary. I better not know anything about it. So it cannot appear on a previous line. You can pick anything that hasn't appeared. A, B, that fortunately there are no constants up here. And so I can pick whatever I want. Now, of course, this is a conditional itself. And so what do? Well, I need to make an assumption. And I need to show FA based on that assumption. That's normal, right? Like we've done this before. This is back right into our wheelhouse. So here, what can I do? I can instantiate. Of course, I can drop off those universal expressions and instantiate. And here I can do it to whatever constant I want. So when I am dropping off the universal, I can drop off and replace those x's with anything I want. If I'm introducing a universal, I have to make sure that the instance that I pick for my calculation, for my method, doesn't appear on a previous line. So if you do this step first, you can drop off universals all you want. But if you did the universal step first and instantiated to A, you wouldn't be able to pick if PA then FA for the universal method, right? Because you would have already had it. So let me say that one more time. Let's say I'm trying to show this, and instead of starting there on line 4 and just saying if PA then FA, I went ahead and just inferred, all right, if PA then GA, right? And then I try to say if GA then FA, right? And I'm just instantiating down here to A. Okay, now I'm thinking, okay, well, I need to show, I can prove this for sure. I got if PA then FA, blah blah blah. There's some logic there. I'll skip over for a second. Now how do I add that universal? Is where my head should be. What should I do there? Well, I've got this method. I can prove universal things. I want to show that. Okay, I want to show the universal. Now I'll pick an arbitrary constant to instantiate to. So I'm like right here now. I cannot pick if PA then FA because it has appeared on a previous line. I'd have to pick something like that. But unfortunately, that's not going to help me out because I don't have any B's up here. You see? So there's a method to the madness here. There's a method to instantiating with the universal introduction method first. So do that first rather than start dropping and instantiating the universals wherever, because you'll just end up having to do that part again. Do this first because there are restrictions on what you can pick for your constants here, not restrictions here. So you can see I can instantiate down to PA then GA here, and I can do the same thing, GA then FA there, and that's going to be, again, that's going to be from line 2, and it will be universal elimination, just as you would expect. I'm going to kind of infer from here if PA then FA, and this is from, I don't forget if we actually prove this, but I'll tell you what the name of the rule typically is. It's hypothetical syllogism. It allows you to infer transitivity across these constants. And now, observe what I have done. On line 9, I have gotten if PA then FA. That is precisely, well, not almost. I guess I could have just shown that honestly without the assumption, but hey, what's the fun in that? I got one more step. Forgive me. I made this a step more complicated than it had to be. But I do have PA, so now I can infer FA here, and that's line 9. That's line 5 and 9. Modus Ponens. Since I showed FA, I can drop that off and do that by direct derivation. And now because I did that on the condition of PA, I showed FA, that allowed me to show if PA then FA. Here's the important part. Because I did this with an arbitrary selection of the universal, I am able to infer based on this assumption that that this applies to everything in the domain. It's arbitrary. Universal derivation. I have shown from universal derivation, this is how I did it. I assumed something held for an arbitrary constant for everything in the domain and demonstrated if PA then FA, which could have been if PF then FF, it could have been if P square then F square, holds for everything in the domain. And now I've proven something, a constraint on the whole domain just based on that assumption and this method. Okay. All right. Let's see. I'm going to do One more, just for kicks. How hard should it be? Not too hard. I'm getting sleepy. Not too sleepy. Just a little. Here's what we're going to do. In the interest of keeping you awake, I'm going to pick something a little complicated, but not too complicated. But something to keep us both on our toes. If there's something F, then there's something that's not G, obviously, as we all know. I'm going to show everything. If it's F, then it's not the case GY. Now, got a universal here, got a universal and a universal. Got Matryoshka doll universals here. What am I going to do? Well, I don't have any constants up here, so I'm not really restricted. So I'm just going to instantiate line 1 over here in the interest of getting this proof going to an arbitrary constant. That's FA, of course. Now, I've got a conditional. So what am I going to do? I'm going to make an assumption here. And then I'm going to drop down the next line. I'm going to say I got to show not G, not for anything, or not the case that everything is GY. That's what I need to show now. So what am I going to do with this? I haven't yet taught you how to play with negations and quantifiers. It's a bit of a trick, but I actually don't need to teach you that here. So what I'm going to do now, because I'm stuck and I can't really do any symbol manipulation, I'm going to assume the opposite and see what happens. So I've assumed that everything is G, Y. Now what? Where am I going with this? Well, I'm going to try to show a contradiction. And what I do have is on line 4, FA, and I am going to go ahead and introduce existential generalization here, and that's going to be from line 4. And why did I do that? Well, it's because if I use line 7 and line 1, then I can get there is something that's not GX. So that's 7 and 1, Modus Ponens. Now, I have this, and that allows me, if I'm thinking carefully, to drop off existential on line 9, as long as I instantiate to a constant that has not appeared on a previous line. B has not appeared on a previous line. So what am I doing? Line 8, existential elimination. What do I have? Well, I have not GB. And remember, I'm looking for a contradiction. I have as an assumption everything is G. Everything including B. Dun dun, dun 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 dun. From line 6, I have universal elimination. Remember, I could instantiate it to whatever I want. I could strip off the universals. And now I have on line 9 and 10 a contradiction. I've shown something has gone awry on this assumption, which means the opposite has to be true. I did that by an indirect derivation. That was, of course, on the assumption of FA, and so I did that demonstrating that if FA, then it's not the case that everything's a G, which is what I was trying to show. Well, at least allows me to make an inference that this holds of everything in the domain, because FA was an arbitrary selection. It could have been anything else. I happen to choose that. So I will continue in class and out of it, but this video, let it serve you to provide illustrations of some of the nuances of the proof calculus we'll be playing with. We'll discuss more in length, of course, in class, but the key takeaway here, other than practice, much like how you get to Carnegie Hall, is that there's a universal introduction universal elimination, existential introduction, existential elimination. A couple of these are easy. Universal elimination, if you have a universal for anything, I'll just use phi x there, you can instantiate it to whatever you want, A, B, C. On the other hand, if you have something of the form A or phi A, you can infer something is phi A. There's the introduction. For existential elimination, if you have something, if you just want to make a move, you can, or you have, well, I guess if you have something of the form, something is phi x, then you can infer phi A if A doesn't appear on a previous line. Similarly, for the universal, if you have something that you need to prove, like show universal, you can assume and then show whatever you need, or actually show that phi A if A does not appear on a previous line. And those are the restrictions for the intro-outro rules insofar as they have them. And with that, I bid you adieu. Take care. See you soon.